All right, guys, let's collect some data. So I'm going to pull the car back to the beginning of the ramp and let it go. And then we'll record some times and put them on the board. So here we go for our first one. 1, 2, 3. All right. And I have time A is 0.0420. Time B is 0.0349 seconds, and time AB is 0.158 seconds. There's our first data point. Set it up again to do a second. All right. 0.0422, 0.0353, and 0.159. Nice and consistent. All right. And trial number 3. We have 0.0421, 0.0350, and 0.158. All right, so you guys need to find the average of those times in your data table. And I'll let you do that. The average times are the times that you're going to use for all of your calculations in the lab. So we have all of the data that we need. We just need to put it into the data table. Then you'll use these averages. Use these averages in your calculations over here. So what is the speed of the car through photo gate A? I'm not going to do the whole thing for you, but that velocity of A is equal to the distance that the car travels when it travels through the photo gate. Remember that, the width of the wing, divided by the time that you measured for photo gate A. So put in your distance, needs to be in meters, and your time that you measured for photo gate A, average, the average time for photo gate A. Then you'll do the same thing for B. So velocity through photo gate B is the distance that it traveled as it goes through the photo gate, divided by the average time we measured for photo gate B. And then the acceleration is that difference between the two velocities. So whatever you got for velocity A, no, B is the final, not the initial, minus velocity through photo gate A. And then you have to divide that by time between the two velocities, the time that it took to go between the two photo gates, which is time AB. You should get an acceleration that is, I don't know what it actually is for this particular set of data, but a reasonable acceleration between, I think, maybe 0.5 meters per second up to maybe 2-ish meters per second, I think should be reasonable. So if your answer falls outside of that range, check your work to make sure that you did it all correctly. And then if you're still not getting it, then send me an email. I'll see what I can find out for you. But it should be in that range. Then you need to take a look at what the difference is between the acceleration that you predicted and the acceleration that you measured. So your measured acceleration, the actual acceleration, is what you got up here for part C. The predicted is the one that we calculated up in number 5. Theoretical acceleration, right here. So whatever your answer is for here, minus whatever you got for number 6, find that difference. What is that difference? Why would we find that difference? What is it that we have not considered at all in the calculations that we did up here? What is always present that could impact the acceleration of the car as it travels across the ramp that we did not talk about yet at all? We've talked about it in other contexts. We talked about this before in class, but we haven't talked about it in terms of the car and ramp right now. So think about that. What is it that could be slowing this car down so it's not accelerating as much as we predicted it would? Now, number 8 gives you a hint about what that might be, if you haven't figured it out already. You're going to use that difference in acceleration that you found in number 7 and use it to calculate a frictional force. Not all of this difference is probably, some of it might be due to friction and some of it might be due to something else, but a lot of it is probably friction. So you're going to use that acceleration, the difference in acceleration that you found in number 7, times the mass of the whole system. So that whole mass that I think 0.4265, I think is what I found, and use those two numbers to find the frictional force in the that's acting on our system. All right, guys, have fun. I'll see you later.